Good morning, students. The last session we had discussed sets, examples for set and representation of sets, that is roster form and set builder form. Okay. Now see some standard examples for set. First example is natural number n. Okay. We read it as natural number n as set of all natural numbers. Okay. Or if you want to write it in roster form, you can write n is equal to 1, 2, 3, dash, dash, dash. Okay, up to infinity. Second one is the well-defined collection, that is whole numbers. We read it as set of all whole numbers. Okay, then write it in roster form, n is equal to 0, 1, 2, 3 to infinity. Then take the integers as we read it as set of all integers. Okay, or you can write z is equal to 0 plus or minus 1 plus or minus 2 dash 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 plus or minus infinity, up to infinity it's there, so I'm putting dash dash dash. Okay, next one is the q. We call it as set of all rationals. Okay, it's not possible to write rationals in a roster form because they do not follow a particular pattern. So you can write q is equal to, in the set builder form, all the numbers x such that x is equal to p by q, where p and q belongs to integers and q not equal to 0. It's a set builder representation of rational numbers. Any number in the form p by q, where p and q are integers and q not equal to 0, we call it a set of rationals. Okay, then the t is there, we call it as set of all irrationals. Again, we can't write irrational as a roster form. Then take the real numbers, caps letter R, we call it as set of all real numbers. Okay, again it's not possible to write real numbers in the roster form. Okay, because again they do not follow any particular pattern. Okay, here you can see n natural numbers 1, 2, 3, after 1, 1, 1 plus 1, 2 plus 1, 3 plus 1, like that they follow particular pattern. Here also see 0, 1, 2, 1 pattern is there. Integers also one pattern is there. But if you check any real number, see, suppose I am taking 1. Can you tell me what's the next real number? No, right? Is it 1.1? No. Is it 1.01 or 1.001 or 1.0001? It's a question mark, right? Why? Because between two rational numbers there exist infinitely many rational numbers. Again, between two irrational numbers there exist infinitely many irrational numbers, or between two real numbers there exist infinitely many real numbers. We can't tell what's the next number. Okay, so it's not possible to write rationals, irrationals and real numbers in roster form. Okay, remember all these number systems are examples for set. Next is cardinality of a set. Okay, see, number of elements in a set is called cardinality of the given set. Clearly set is given means that set has some elements, right? Okay, if you count the elements you can find some number of elements, right? Okay, number of elements in the given set is called cardinality of the set. Suppose set A is equal to, see, 1, 2, 3, 4. Okay, it's given. Okay, here see number of element of A, n of A. N of A means number of elements in the given set A, or we call it as cardinality of A is equal to, just count the numbers 1, 2, 3, 4. Okay, or take a is equal to 2. What is n of a? N of a is equal to only one element here, you can see, right? So n of a is equal to 1. Okay, suppose see, set a is equal to 1 3 5 7 8 9. Okay, what is n of a? N of a is nothing but cardinality of a. Cardinality of a means number of elements in a given set. How many elements are there? 1 2 3 4 5 6, right? So here you can write n of a equal to 6. Clear? Cardinality of set a is nothing but number of elements in the given set a. Okay, these types of sets, under that, first one is the null set or empty set. Okay, definition says a set having no elements is called a empty set or null set, and is denoted by, okay, you can use this symbol, only flower brackets, or this symbol. Okay, this bracket without elements we called it as empty set, or this symbol again represents the empty set. See, set having no elements. Okay, no elements means it's empty, right? So we called it as empty set. Okay, for example, see, all right, prime number less than 2. Okay, you need to write the prime number less than 2. Take it as set A such that set A equal to, is there any prime number less than 2? No, right? Prime numbers are greater than 1. Okay, and your prime number starts from 2 only, right? There is no prime number less than 2. We defined one set, but there is no element. That time we can write is A equal to empty set, or A equal to this symbol. Or see, set B such that even numbers between 2 and 4. Okay, then you can write B is equal to, is there any even number between 2 and 4? No, right? We can't find any even numbers between 2 and 4. So B is equal to empty set, or you can write it as B equal to empty set. Or take the third example, set C such that natural number or natural numbers less than 1, natural number less than 1. Then you can write C is equal to empty set Y, natural number n that starts from 1 2 3 up to infinity, right? Again, see, these are all examples for empty set. Just to remember, the set having no element is called as an empty set, and it is denoted by this symbol. Okay, now check the example. Suppose I am taking set A is equal to, okay, like this. Is an empty set? No, right? A is not equal to empty set. Why? Because here 0 is there, one element is there, right? 0 that belongs to A. What's the definition of empty set? Set having no element. If 0 is there, see, set has one element, that is 0. That time it's not an empty set. Okay, empty set means the set having no elements. Okay, so if A is equal to like this, or A is equal to like this, then only A is empty set. Or if you take A is equal to 0, or A is equal to 1, like this, see, here you can see one element, that is 0. Here you can see one element, that is 1. Okay, these are all not examples for the empty set. Okay, right, not equal to empty set. Okay, set having no element, then only we call it as empty set. Next is singleton set. Definition says a set having only one element, okay, called as singleton set. Okay, name itself says, right, single. Okay, singleton, that means set having only one element. Okay, that time we call that set as a singleton set. For example, see, set A is equal to 1. What is n of A? Cardinality of A equal to 1 only, so it's a single set. Or A is equal to, see, suppose I am taking 10. Okay, how many elements you can see? Here you can see only one element, right? Here I'll write n of A equal to 1. So whenever number of elements of the set A is equal to 1, we call it as singleton set. Or take set B is equal to like this. Okay, how many elements are there? 0? No, here one element is there, that is 0. Here you can write n of B is equal to 1, right? So it is an example for singleton set. Okay, or take set A is equal to like this, empty set. What is n of A? Number of elements in the empty set, it is 0, right? Okay, so it is not an example for singleton set. Okay, set having only one element, we call it as singleton set. Here set has no element. No element means we called it as empty set. Next is finite and infinite set. Definition says set having finite number of elements is called a finite set. Otherwise it is called a infinite set. Otherwise we call it as an infinite set. Okay, if a set has finite number, finite means countable number. Okay, if your set has the finite number of elements, we call it as finite set. Otherwise, that means if your set has no finite number of elements, then we call it as infinite set. For example, see, your let set A such that natural numbers less than 100. Okay, what's the possibility n of A? N of A is equal to 99, right? Natural number starts from 1, less than 100 is given. Less than 100 means up to 9. Second set B, I will take natural numbers. Okay, we know, right? Natural number n means 1 to up to where? Up to infinity. First one is an example for finite set. Okay, second one is example for infinite set. Okay, if your set has finite number, that means countable number of elements, we call it as finite set. If your set has infinitely many number of elements, we call it as infinite set. All number systems are examples for infinite set. If you take integer, infinitely many integers are there. Or if you take real number, infinitely many real numbers are there. Okay, so your number system is an example for infinite set. Okay, in a natural number, you can restrict the numbers, or here I'll take C, set C such that integers less than 2. Integer less than 2. Tell me the integers less than 2. Is it a finite set or infinite set? Integer less than 2 means you can take 1, 0, -1, -2, -3 up to where? Up to minus infinity. So this is an example for infinite set. Okay, or take set D such that natural numbers greater than 100. Natural numbers greater than 100, you can write 101, 102, 103 up to where? We don't know, right? Up to infinity. So this is an example for infinite set. Natural numbers less than 100, that is an example for finite set, because we know natural number starts from 1, but natural numbers greater than 100, we can't find the end, right? We don't know where it will end. So natural numbers greater than 100 is an example for infinite set. Okay, just to remember, finite set means Set having finite number of elements or countable number of elements. Infinite set means set having infinitely many number of elements. Next is equal sets. Two sets A and B are said to be equal if they have exactly the same elements. Okay, two sets is said to be equal, then they must have exactly the same elements. For example, see set A, I will take it as 1, 2, 3, and I am writing set A is equal to set B. Question is find set B. Since set A is equal to set B is given, by the definition A and B are equal, then see they must have exactly the same elements. Okay, this implies set B also is equal to 1, 2, 3. Okay, in this case you can say, right, n of A is equal to n of B. Moreover, it has the same elements. Okay, equal means name itself says na. So two sets A and B are said to be equal, then they must have exactly the same elements. Okay, next is equivalent set. Okay, see two sets A and B are said to be equivalent if number of elements of A is equal to number of elements of B. Okay, here see they may have exactly the same element or they may not be have exactly the same elements, but if number of elements in set A is equal to number of elements in set B, then we call that two set as the equivalent set. See, there is a difference in equal sets and equivalent sets. Equal set means A and B must have exactly the same elements. If they have exactly the same element means they must have exactly the same number of elements. But here see equivalent set. For example, I am taking A is equal to 1, 2 and B is equal to 3, 4. Okay. Clearly A is not equal to B because here 1, 2 element is there, here 3, 4 element is there. Okay, but check n of A, n of A is equal to 2, n of B also is equal to 2. Here n of A is equal to n of B. That implies A and B are equivalent. Okay, then see, take the second example. Suppose A is equal to 3, 4 and I'm taking B also is equal to 3, 4. Okay, here see A equal to B. A and B are equal sets. Moreover, n of A is equal to n of B. That means two sets are equal. That implies they are equivalent. But see, if you observe A is equal to AB and B is equal to CD. Take element C, comma D. Okay, n of A is equal to n of B. Okay, but A is not equal to B. Okay, that means A and B are equal sets. That means they are equivalent. But A and B are equivalent, right? Here A and B are equivalent because n of A equal to n of B. That does not implies A and B are equal sets. Okay, so see, remember equal sets that implies equivalent. Okay, but equivalent doesn't implies equal set. Okay, in some cases equivalent set may be equal to equal set, but in generally all equal sets are equivalent sets, but equivalent sets are not equal sets. Okay.